Okay, thank you. So, welcome all. My name is David. I'm a PhD student from Germany, and yeah, I'm going to present our paper on verifying secret control flow elimination. So it's about secure compilation again. So let's motivate it a little. So there are estimations, I'm not sure how good they are, but there are estimations that the annual damage made by cybercrime globally is around 10 trillion euros. So for the locals, that's around 1.4 quadrillion Icelandic krona. So it's a lot. Yeah, and of course, hackers exploit all kind of vulnerabilities in software to achieve this. And one common kind of attacks are side channel attacks. So a side channel attack is one where the attack is not possible because of a bug or an incorrect implementation, but because some secret information is leaked through a side channel. So a prominent example are timing side channels. So here's a function that that compares a password to a user input, character by character. And the password is marked in red here because it's secret. And so the problem with this code is that the amount of time that it takes to execute depends on the password, also on the user input, because, well, depending on how long the prefix is that matches, the program returns sooner or later. Yeah, and so normally that's not a problem, but if an attacker has somehow access to the device where the code runs on and can measure it, they can just throw many different inputs to the function, measure how long it takes to execute, and then recover the secret password. And so, yeah, this may seem like a theoretical attack, but it's actually doable in practice and has been shown that several crypto implementations, like Diffie-Hellman, for example, as we've just seen, the old implementations all had this kind of timing side channel. And so there have actually been attacks using this. So it has been a topic of research since like 30 years maybe, and it's still relevant today. So for example, in the last year, there have been reported 25 new timing related vulnerabilities on CVE. Yeah, so it's still a relevant attack. And here I'm going to give another example. Here it's a bit simpler. There's just a condition that depends on some secret, and the two branches of the condition take different amount of time to execute because, well, this cosine and power is just more expensive than the addition. And so there's one simple thing that we can do in this case. Okay, first here's a control flow graph of this code. We can do if conversion, which is a very old technique, and it's just consists in we execute both branches sequentially, and then we predicate the assignment here using this select operator. So we see that the structure of the control flow graph changes. We execute both branches, and now this code is linearized. And yeah, the code on the right is now constant time, or at least the execution time doesn't depend anymore on this secret parameter. Yes, and so that's our goal here, that the branch decisions should be independent of any secret parameters. That's the goal of having this control flow security. And so there have been advancements made on this simple if conversion. So one recent advancement, one algorithm that we're looking at here is called partial control flow linearization, or PCFL. I'm not going to explain how it works in detail. Just the idea of PCFL is that it only linearizes the conditions that are necessary to linearize. So in this case, only the condition at 1, which is secret, is linearized. And the edge from 1 to 6 is removed. But the public condition at vertex 2 is left intact. And now, if we apply this PCFL, we get a function that we call detour. It takes an edge in the original graph, and it returns the vertex, which is the new target of this edge. So for example, the edge from 1 to 6 is changed to 1 to 2, which means the new target of, the detour of 1, 6 is 2. And similarly, the edge from 5 to 8 is changed into 5 to 6. And there's now one important property that we can show about PCFL. So for any edge in our original graph, the original target of the edge post-dominates the new target. So for example, 6 post-dominates 2. in the transformed graph. So what that means is just that every path starting from 2 will eventually reach vertex 6. Okay. And now there exists, in recent years, there have been developed quite a few tools against the timing-related vulnerabilities. So there have been developed some constant time compilers that all in some way or another try to mitigate such the non-constant time problems. So for example, they apply if conversion or other algorithms. There have also been PCFL-based constant time compilers. And well, these are very great tools, but there is one problem with them. I mean, here we are at an ITP conference, and so the problem is that these implementations, while they may be correct on paper, they are not verified. So these can be complex transformations, and so the problem is they may introduce bugs into the program. So actually, I have played around with one of these implementations, or these tools, and so for some special case where a loop index was reused after the loop, the code that was generated it behaved differently than the original code. So of course, that's what we want to avoid. And so our question was whether we can formally verify such a constant time transformation. And to do this, we use ComCert. ComCert is a verified C compiler written in Rock. And so it works like a normal compiler. Basically, it starts with some C or source like language, and then through various transformations, it goes down until we have an assembly language. And so all of these intermediate languages have some different kind of purpose. And now the verification works by equipping each of these intermediate languages with some small step semantics. Yeah, so small step semantics is very similar to actual execution on a machine. So in contrast to big step semantics, where we have something like execute loop or execute a function, in small step semantics, it's like a step-by-step execution. So execute operation, go to the next vertex, execute operation, and so on. And then for each of these transformations, the semantic preservation or the correctness of the transformation, it's proven via a small step simulation diagram. So we have seen it already, but I'm gonna give you a quick example of how it looks. So here we have a transformation from language I to language I+1. And on the left side, we have a single step from state 1 to state 1 prime. And now on the right side, we have the state 2 that is in some way equivalent, or it matches the state 1. And now if we can say for this single step in the first language, there exists one or multiple steps in the second language to a state 2 prime, such that this final state 2 prime matches the state 1 prime again, then we have a small step simulation. And now this means that every execution in the first language corresponds to a similar execution in the second language. And then from this, it follows that it is shown for each transformation. So it follows that the full compiler pipeline is correct. So the behavior of the assembly code is the same as the behavior of the original C code, equipped with some semantics. Okay. And now let's come to our contributions. So we verified a constant time compiler transformation, so PCFL, in ComCert. With a little restrictions. So we only did it for a small subset of C currently. So to be precise, we only consider a single function that doesn't call other functions and also doesn't have any loops. So yeah, it's quite a small subset of C, but it's still a quite complex verification. And the reason is that this transformation, the PCFL transformation, it's a global transformation. So it depends on the full control flow graph. And also, changing a single edge in the control flow graph may completely change the behavior of the program. And also we eliminate secret control flow. So there are other kinds of timing dependencies like cache effects, but we're only looking at secret control flow. And actually, we do two things here. So first, we show that our transformation is correct. like we've just seen, that the semantic preservation is given. And then also we show that the transformation actually does what it is supposed to do. So actually it removes all secret control flow. So we show these two things in a second. Okay, so our approach is the following. Here again, we have the pipeline of ComCert. And in the middle, you see RTL. It's just some intermediate language that it has a control flow graph for each function, and it works on pseudo registers. So we have an infinite amount of pseudo registers, and then the operations work on these registers. And we do a transformation from RTL to RTL, which is actually split into two transformations. So the first step is we perform this PCFL algorithm. So we do the graph rewriting. And then in the second step, we do the predication of assignments. And therefore, we introduce this new intermediate language, which is called pred-RTL. And here you see the graphs of these intermediate languages. So we begin with the original graph, GOIC, and we end with our transformed graph, GPCFL. And now the intermediate representation we introduced, the specialty here is that it has both graphs simultaneously. Yeah, and I'm going to show you how this works now. And yeah, now let's look at this first transformation, the PCFL transformation from RTL to pred-RTL. So first here we have the small step semantics of RTL. So in RTL state, in a simplified form, it has this vertex, so the program counter, and then a register set. So the register state is just a mapping from registers to values. So values are like integers or 64-bit values. And this is our simplified RTL state. We're not looking at memory or a call stack here at the moment. And the execution just looks, for example, like this. We start at our initial state at 1. Then we go, for example, to 6, go to 7. And in each of these steps, we may change the register state until we hit the end. So it's just a basic small step execution. And now, this is the semantics of pred-RTL. So here, the state doesn't only consist of the position in the original graph, but also simultaneously of a position in the transformed graph. So our initial state is the state 1, 1. We are at position 1 in both graphs. And we call this state live because the positions are the same. And now the next step, well, in the original graph, we go to vertex 6 because that's what the condition has made us do. But the transformed graph, we only have one edge to vertex 2. So here we can only go to vertex 2, and now we are in the position 6, 2, which is a dummy state. And now if we are in a dummy state, we continue moving, but only in the transformed graph. And if we are in a dummy state, we do not change the register values. So now the registers stay as they are until we come back to this live state, which here is 6, 6. Now we are at the live state again, and here we can normally continue execution until we reach the end. So you see a single step of RTL may correspond to multiple steps of pred-RTL until we reach a live state again. Now we have to define a matching between RTL and pred-RTL semantics. This is pretty straightforward. So our initial state 1 and the state 1, 1 match. So they're equivalent, given that the registers are the same. And then if we go to this dummy state, 6, 2, it doesn't match any RTL state. Now we continue executing until we hit this live state, 6, 6. And this matches the RTL state at 6, given that the register values are again the same. And so this is also the rule that only live states in pred-RTL match an RTL state. And with this definition of the pred-RTL semantics, we can show that the simulation, that this transformation is correct. For this, there are two more things that we have to look at. So the first is dummy states must not change the register values. So in our pred-RTL semantics, this is something that we can just define. So we can just define a pred-RTL state registers are not changed if the state is a dummy state, because, well, we have access to both positions at once. So, but then in the next transform, in predication, this is actually implemented. The second thing is, that's important, a dummy state must always return back to a live state. And so we have just seen this. We will always come back to a live state, and this is guaranteed by this lemma from before, from PCFL, that for every edge, the original target post-dominates the new target. So this just means we will always come back to the original target. But then there's one thing that we have to take care of. So during this detour, the program must not crash. So how could this happen? Consider the following program. Here we have the scouted division by 0. And in the transform program, if t is equal to 0, then during this detour, we compute this division 1 divided by 0, and now our program crashes. And yeah, this is bad. And how? What can we do against it? So we chose to do a very simple thing. We just restrict ourselves only to safe operations. So we only allow safe operations in the program. A safe operation is one that will never crash and will also never introduce undefined behavior. But we don't have to be that restrictive. So actually, we can relax this restriction to the non-uniform vertices. Non-uniform vertices are all those that can be accessed during a detour. So we can show, yeah, for the vertices that are never active during a detour, we don't have to do this restriction. Yeah, if we do this, then we can show that our transformation is correct. It doesn't introduce any bugs, and the behavior is the same as before. And now let's look at the second transformation, the second part, from pred RTL back to RTL. So yeah, let's consider this assignment. So we have this operation, and we assign it to the register dest. We are at vertex 5 in the original graph, and the successor is vertex 6. So what do we do now? The thing is, we want to get rid of the original graph, because in the end we can only have one graph in RTL. So we have to get rid of the original graph somehow and go to the transformed one. And now the first thing that we do, we check whether we are at a live state. And for this, we have this VORIC register, which we introduce. So the VORIC register, it contains this VORIC position. But instead of storing it in the pred RTL state, we now store it in a register. And we check, okay, if VORIC is 5, then the current state is live. If not, we are on a detour. And then we actually do the predication of the assignment. So we execute the operation, and then we assign the result to dest when we are live. Otherwise, dest is left unchanged. And now we know that this execution of the operation, it doesn't crash, because we have just had this restriction on the safe operations. So we know that this operation, it always succeeds. And then the last thing is we update our VORIC register. And now it works as follows. If we are at a live state, then we know that the original successor of 5 is 6. So then the new VORIC register is 6. If we are not in a live state, we are on a detour, and then VORIC doesn't change, because then we have to wait until we get back to a live state. Yeah, and then the successor of this vertex 5 will be the new successor, so detour of 5, 6, which is the new successor in the transformed graph. So by putting this VORIC position in the VORIC register, we actually put the structure of the original graph into the code, because you see these 5 and 6, this is now in the code. And we are left with the transformed graph in the RTL that we have produced now. And also, there is no need for a Boolean predicate with this approach that we chose, because normally when doing this predication, we need a Boolean predicate which somehow depends on all the conditions that were before. But now we are only comparing this single position with statically known values. So it's a very simple way of doing this predication, and it works. Okay, and with this predication, we can prove it correct, and then we have shown that our constant time transformation is correct. So that's the high-level overview. But yeah, now there's one thing left. So we also wanted to show the control flow security, so that the transformation actually removes secret-dependent control flow. I'm just going to restate the statement here. So here we have two executions of the same program that have the same public parameters, but have different secret parameters. And these two executions both go to a final state. And these traces, these mean the sequence of traversed program points, or the sequence of traversed operations. And now what we wanted to show is that these traces are the same. So the same sequence of operations is performed, possibly with different values, but the same sequence of operations is performed if the program is run with the same public parameters. And yeah, we have shown this for our pred RTL language. What we haven't done is to take this proof and pull it all the way down to assembly. So we could do this in the future to actually show that the resulting assembly also has this property. But yeah, this should be doable. And okay, with this, I come to the conclusions already. So it is possible to verify a constant time transformation for a subset of C. It is possible, but it's still a lot of effort. So we have added 9,000 lines of code to ComCert for doing this. And so in the future, we may look into tackling the remaining challenges. So to apply this approach also when there are function calls and loops in the program. But the question that open question we have here is if small step semantics are really a good tool, especially for such a loop transformation, we may want to look into other semantics where it can be modeled in a better way. So maybe big step semantics, we may look into this in the future. And with this, I thank you all for listening.